everyone, and welcome to Talk Nerdy. It's Monday, February 13th. Happy early Valentine's Day. And I'm your host, Cara Santa Maria. I want to thank those of you who made Talk Nerdy possible this week because, as usual and as always, Talk Nerdy is and will remain 100% free to download. The only reason that's possible, because I am Talk Nerdy's only employee, is because of contributions from listeners like you guys. So those of you who want to pledge your support, you can do so by visiting patreon.com/talknerdy. This week's top patrons are Mark Hepburn, Phil T-Bear, Timothy Glover, Pedro M. Rosario Barbosa, Christian Jeffrey, David Lacer, Jeffrey Perez, Stuart Ogue, The Honorable Husband, Charles Payet, Jafe, Gabriel Felipe Jaramillo Gonzalez, Brian Holden, and Jeffrey Sewell. All right, I'm excited to dive right into this week's episode because it's a really fun one. I was honored to be able to be joined by Helen Czerski. Now, she hails from the UK, but she was visiting the US, so we were able to talk in person, in studio. She is a scientist and a television presenter in the UK. Her research actually focuses on the optics and acoustics of ocean bubbles, and she's interested in the influence of ocean bubbles on the atmosphere. She wrote a book recently, and it was just published in the US just last month, and it's called Storm in a Teacup, The Physics of Everyday Life. So once again, here she is, Helen Czerski. Well, Helen, thank you so much for joining me today. I'd love to say for coming all this way across the pond just to sit down on my podcast, but of course you're not just here for me.
Well, I could be. Let's pretend I am.
So you are obviously you've lived in the US, but obviously everybody I think can tell based on your voice that you're from the UK. Do you live in London?
I do live in London now, yeah. I'm from Manchester in the north, and then I lived in San Diego and in Rhode Island here for a few years and a few other places, and then now I'm back in the UK. So I've moved. Scientists move about a lot, right? That's one of the nice things about being one. So
it's true. It's true. I wonder what people. I'm starting to develop more of an ear for accents. I spent a little bit of time in Manchester this past year for a skeptic conference, and I've had a couple of people on the show. Well, I don't know if a couple have been from Manchester, but at least one was like a Merseyside person, and that is a very particular accent, and I hear a hint of it in you, but it sounds like you've been in London a while.
Well, you also, depending on who you were talking to, right? If I was speaking like this, you'd hear it be quite different, but I'm not, so it's all right.
Right.
It's like kind of, it's like you speak in the way that makes the person you're speaking to most comfortable. So you do adapt. There are situations where I will put on a slightly more British accent when I have to be polite.
Gotcha.
So I'm not an accents person, but it goes with the, you kind of mirror the person you're talking to a little
bit.
So
a lot of what you do in your career involves what you guys call television presenting, what we call here hosting, which I hate. I've actually borrowed against kind of the British way, and I like to call it presenting as well. It sounds a lot less, I don't know, reality TV to me. But do you have to put on sort of a very neutral accent here in the States?
I've never been aware of it.
Really?
Ever. No. And occasionally, when I first started to hear myself recorded, I heard a Manchester accent in the recorded voice that I don't hear when I'm speaking. And I have occasionally had directors say, "That's a bit Manchester, Helen." But no, it's not. It's never been an issue, and I wouldn't. I mean, you can't put it on. The way I speak is the way I am, and that's all right. But I'm quite proud of being from the north of England, and it's only recently realized that I kind of made the connection with the science, because the northwest of England is, when it comes to the start of the Industrial Revolution, the technological revolution that we've been, through over the last few centuries, Manchester is right at the hub. We built the first canal, the first railway station was in Manchester. I grew up surrounded by the sort of litter of 3 centuries of industrial history. My mum worked at, my grandfather was one of the first television engineers. There's a big industrial park near Manchester called Trafford Park where they built a lot of stuff for the war, in the Second World War. And then, there's always sort of mechanical things. And then my mum worked for Ferranti as a computer programmer, and Ferranti were obviously in there with early computers. So you start to look back. And I only did this 6 months ago because of the book. And you go, actually, I grew up in an environment where understanding how things work was taken for granted. People went and did
Mm-hmm.
things. It was very practical, and you saw this was what made this thing work. This is what a steam engine is. And I only, you move to I moved to other places and you go, oh, everyone else doesn't have that. They don't grow
No.
up with, cogs and bits of steam engine and, the sort of lifts and things near the canals and the warehouses in Manchester. And those paintings of L.S. Lowry, which show the industrial, they didn't make it look very nice, to be honest. It's all a bit grey.
Yeah.
But, these were people that were cogs in the machine that helped build the modern world. And so it is there that, the cultural influence, which is nice. And of course, lots of places contributed. I'm not saying Manchester has everything, but there is a lot of science and technology in that region, and there historically has been for a very long time.
And it is important, I think, that that the culture sort of work its way into the consciousness, because it's true. I don't know if it's everywhere in the States, but it's definitely, I think, a mentality that you see in the States. And I wouldn't be surprised if it's the same in London, where people do just quite take all of their technology for granted. There's not a real understanding of how things work and why things work. And because there's no true understanding, I don't think there's that much respect or appreciation for, I'm walking around with my iPhone in my hand. Oh, it's just a thing I can throw away and buy a new one. Well, no, it's not. There's, it's so important to, I think, respect what went into this and the genius of it, the manpower and the raw materials and all of the bits and pieces that were involved. It's gotten a little too easy for everything to be a little too disposable, I think.
It's basically like magic. And it is the lack of
Yeah.
appreciation is a funny thing. A couple of years ago, I was at the Manchester Festival of Science Industry, and my family had come along because I was speaking. And a friend of mine who talks about, Matt Parker, who talks about maths a lot, he'd made a domino computer, which was a brilliant thing. So he set up, they spent like 4 hours building just this complicated domino thing. And what happened was it added numbers together in binary numbers. So you'd throw all the dice and pick two numbers, so maybe a 3 and a 5, and then you'd knock over on two different bits of the dominoes, a 1 and a 2 for the 3 and a 4 and a 1 for the 5, and you'd watch the signals. So the ones added together to make a 2 and the 2s added together, as these little dominoes were running around, and at the end some dominoes fell over and it gave you the answer that it was 8.
Love it.
But you'd actually watch it happen. And so we're all there. My mum had been a computer programmer. We just think it's the coolest thing possible. And my cousin's kids were there, who must have been maybe 8 and 10 at the time. They were like, what is this? And we're like, this is, when you do your phone, you've got this is the only thing that is happening inside that phone. Fundamentally, this is it. And they were like, whatever. And I swear, by the end of this, they were surrounded by like 8 adults just going, but this is so cool. And these kids were like, can we go and have tea now?
Right, right. Yeah.
And it was such a sort of, they're the first step, which is too far away. My grandfather and the mechanical engineers, they saw things go pop and bang, and electricity was like a sort of beast that was there. And my mum's generation, the computer programmers, they saw what it made possible just in there at how the bits worked. And now it's just, what else would you do? They were like, these kids just touch the screen and it works. What are you talking about?
Exactly. And it's almost like not good enough still.
Yeah.
New things come out so often that are like, in the truest sense of the term, amazing, awe-inspiring, mind-boggling. And it's just sort of, oh, yeah, of course it does that.
Yeah,
Like,
or
when's
why
the
doesn't
new
it do
one?
that?
Exactly.
Why does this not? I can talk to someone on the other side of the world. I can send them pictures and everything, and it's instant, and they're on the other side of a huge planet. But why is it drop the call?
Exactly. Yeah, it's just.
But I think
there's like an entitlement that comes with it.
But that appreciation. Also, someone's got to keep building them. That's the other thing. It's someone has to keep putting the bits together.
And luckily, I guess it doesn't seem like there's a big shortage of at least a core of individuals who are fundamentally interested, who want to continue the education and push the boundaries of what's even possible and create and make and be ultra creative in their, science and engineering endeavors. But, I worry sometimes that there won't be enough if we can't inspire individuals to do it. And it is hard, that's kind of the sort of the holy grail of what people like you and I do, which is, how do I tell these science stories and how do I investigate what's going on in such a way that it makes not makes, but it interests people who are watching who maybe don't have exposure to that very often, that it inspires them and that it kind of, even in some small way, improves their what we call science literacy.
Yeah, appreciation is it's a continual, because people are interested in different things, and that's all right. I'm interested in science. You're interested in science. There's lots of other things to be interested in, but it's and you're continually fighting for space in a very mixed world. But things like the
Absolutely.
maker community are brilliant, and the fact that there's this huge, this weird thing that we have more information accessible about how the world works than we have ever had for the first time in human history. The frontiers of knowledge are not inaccessible. They might be incomprehensible, but you can absolutely Google something and go right to a piece of information, and that's a huge, another one of those huge achievements. And yet, we don't necessarily use it well or go looking for it.
It's true, and the only real barriers for many people is simply a lack of interest.
Yeah.
There are ways, especially I love that you mentioned the maker community, because there's sort of a scrappiness to the maker community that I quite respect. Like, you almost don't even need money. You almost don't even need any means to get together and to just, I've met makers who do incredible work with garbage, with broken bits and pieces. They'll put them together in new ways, and they'll come up with, ultra creative, artistic kind of feats of engineering, and it's brilliant.
But the key thing is the critical thinking and the creative thinking. It's not the equipment. And that's one of the other things that I think in the sort of glamorization of science, like, oh, it's big facilities and technology. You need a very shiny building, and you need this kind of specialized equipment, and it makes it all very distant. And I think the pendulum is starting to swing back, because it's becoming, the closer it becomes to magic, the more inaccessible it becomes. And now there is, fundamentally, it's still people having ideas.
Yeah.
And the history of humans doing things has been just people going, oh, I wonder what happens when you do that, and you use critical thinking and evidence, and then work your way through a problem. And it's, what worries me is that people might be losing touch with confidence to do that, because everything's just so complicated and difficult. Leave it alone. I've got other stuff to be doing. And that's why I care very much about the everyday little bits, and the sort of physics I talk about on TV and on the radio is the physics of the everyday world. They've got the sort of quantum and cosmology, which is quantum mechanics, which is very small and very weird, and you've got cosmology, which is up there and far away and difficult. And people think those are the frontiers of physics, but there's a third one in the middle with the classical physics laws. And it's just how those laws, build complex systems, how you build the world out of classical mechanics and rotational dynamics and a bit of thermodynamics, and the rules are the same, but they manifest themselves in complex ways. So, the bubbles that I study in the ocean, that's my research topic, is the bubbles underneath breaking waves that are helping the oceans breathe. All classical mechanics. You can, all the bits of physics you need to solve that, you can write down quite simply. It's just that there's so many of them, and it's so complicated that that we're still discovering things, and that's an area of current physics research. But you only get to that by looking at the everyday little things. So it's like they're making these bridges between accessible bits of science, because the same patterns explain these big complicated things, and it's really important we don't lose that link. That the far away, complicated, amazing technology still exists in the same physical universe as me knocking toast off a table.
Yeah.
The same rules apply.
And these are rules that are kind of, as you mentioned, fundamental, relatively simple to illustrate, to visualize, and kids learn at quite a young age, or at least they start to learn the building blocks, the foundations of them at quite a young age. I do think it's quite important to see individuals like yourself in that capacity, especially on television, which is where most, I think, young impressionable people get a concept of the world. They get a sort of relational understanding of who does what and what roles are available to them, and to be able to see a strong female physicist on television talking about these things with a lot of passion, talking about them in a way that really shows a deep love and fascination, is huge. Because I know when I was little, that wasn't a career option for me. I mean, I knew I wanted to be a scientist when I was quite young, and then I lost that, but I always wanted to be a paleontologist. That's my own thing, as evidenced by
we
my
are
crazy
surrounded by dinosaurs.
Exactly. And then, I got away from it, and math is hard, and I don't know about science. That might not be the language I want to speak, and let's go these other routes. And then eventually it came back, which was great. I think it was for me in the cards, but for a lot of kids, when they first first start to turn away from it, they may never come back. And so I think it's really great to see that example being set day in and day out. Were you the type of girl when you were in school and when you first started studying these things that just kind of always knew, or did you struggle with some of those same sort of identity issues or fear? For me, I think it was more of a fear. I think that's the case for a lot of little girls. It's like, oh, I might not be very good. Math seems hard.
So the first thing is in the house I grew up in, my mum was the computer programmer. My dad was the one who couldn't boil an egg. I mean, he's good at, but his family were more sort of literature and reading. And so I grew, and I have a sister, but I don't have any brothers. So I grew up in an environment where, in this technological place where lots of people have got jobs doing science. So it never occurred to me that I couldn't do maths. And my mum used to teach me maths on the whiteboard, actually, there's a kitchen whiteboard for shopping lists. And occasionally she would teach me what pi was when I was quite little. And so I never had the doubt. I just did, I just went to school, I just studied it. And I never really thought about any of it. I was always interested in ideas and reading. The only time I remember consciously thinking about it was, so I went to the university, I was at Cambridge, and the degree there, you don't go to study one science topic. There's this thing called natural sciences. So in the first year, you study 3 experimental sciences equally, and maths. And even if you, like me, you go to do physics, so I did geology and materials science, and it's actually brilliant. It's a brilliant system because quite a lot of people, they don't know what geology and materials science are, and they don't really know what physics is. So you get to have a go at 3 on equal footing, and then, you might be a geologist instead. So that was brilliant. But I remember filling in the form to get from the first year to the second year. You had to choose your options when you start to narrow down. And I do remember, I must have been in the Cavendish laboratory, the physics laboratory at the time. And I do remember looking around me and going, looking at the physics box and going, do I really want to spend 3 years with these people? Just not because they weren't, but just, that there was and there is a stereotype that does exist for a reason.
Exactly. Yeah, it's not everyone, but there are enough.
So that, I do remember that. And I ticked the boxes. I was going to do physics, and I was very independent. I didn't really care what people thought. And even I was like, so it wasn't about I can't do it. It was more about I'm choosing to be spending my time with these people who are not really like me in character. Although there's lots of great physics friends over the years. So, but apart from that, I think but it's very interesting now talking to, schools groups and especially teenagers. And when you get a really good group and you get to the point where they'll actually ask you questions they're really thinking about. And the questions are, like you just said, what if you can't do it? And then the next question is always, do you have a boyfriend? Which I find very depressing. I mean, at teenage, whatever, they're thinking, they're discovering hormones for the first time. And they're suddenly aware of all these social relationships. They're all very difficult. But there is a sort of, that's the other thing, how does society view someone who does that thing? And there are some big battles there that are still very uphill, and it's getting better. But
absolutely. And those things actually work their way into the individual. When society has such a strong view, point of view about a certain stereotype, it's reflected in ourselves. I've had multiple people on over the past few weeks on the show where we've talked quite a bit about stereotype threat and things like that. And we have these implicit biases about ourselves. So I have many friends who are brilliant scientists, who studied at Caltech, which is one of the most competitive institutions here in the US, and who have done incredible things and wonderful accomplishments, who do struggle with some of the kind of more core social skills, just being in an academic bubble for quite a while and then struggling with really knowing how to kind of venture out on their own, or adulting, as they call it, and
it's a new verb, that isn't it? It's popped up in the past few years.
God. Yeah. And a lot of times I just want to shake them and be like, how to do this. Everybody has this inside of them. Yeah. Don't let your idea of what you're supposed to be like as a scientist define you, because they kind of give into this, I'm a fumbly, incapable.
Yeah, it's dismissive. They almost dismiss
exactly.
themselves.
And I don't need a boyfriend is not in the cards for me. And it's like, what are you talking about?
There's an excellent book that you may have read called Delusions of Gender by Cordelia Fine, which is, I absolutely recommend it to all of your listeners, but it specifically deals with gender, but it talks about the sort of socialization of society, how people grow up with expectations, and there's all these little things in there about even tiny little cues. That's all it takes for your brain to go, I'm supposed to behave like this. and which is kind of depressing because we're stuck with it. And the important thing is that, the book is about women and the position of women in society. But what I see now is more and more very stressed men trying to live up to the fact that they think they're supposed to be the breadwinner and they can't show emotion. And that's causing just as many problems. And there's this whole, we need to just open up and let people, and that in science, in some ways, science is very good for that because, and that's what's one of the nice things about the internet thing is that anyone can go online. You can look up a YouTube video. Like maybe when I was a kid, if I wanted to learn woodworking, I had to walk into a woodworking class and I would be the only girl.
Yeah.
But now you can look up a video on YouTube and you've no idea who else is watching it. So things are becoming more accessible.
It is in many ways a great equalizer. It's funny because historically we don't think of it as such because it was so gender defined and so siloed. But really there's nothing fundamental about being a girl or being a boy that in any way affects your scientific ability. There really is no true gender divide. It's all an illusion because of history. But functionally, it absolutely does not matter. But
and it's the same. So there's a thing I did a couple of years ago in Arizona where I was filming a documentary on the sun and the BBC wanted me to do some arc welding to talk about heat. And so I rock up at this proper old school welding place in Arizona, very, very much the middle-aged men with the beards and the
like they don't have masks in your size. They don't have gloves in your size.
So this guy's like, oh, well, he was very nice, but basically here's a little girl, let's teach her how to weld.
Yeah.
And so it turns out I am brilliant at arc welding. Now, this is not because I'm particularly good at things. It's because my mum basically taught me to do it when I was 5 with icing cakes. Because if you look at the way you hold a welding thing, with your left hand, you're guiding the nozzle. With your right hand, there's a thing that you squeeze, which makes stuff come out. It's exactly the same as icing a cake, except one involves hot metal at 2000 degrees and one involves sugar. And so people are like, oh, well, the one with the metal, that's technology and men do that. The one with the sugar, that's just little girls messing about in the kitchen. And there's also that women do technology if you look at sewing and cooking. And these are technological pastimes or, the skills. And it's just that the label technology is given to the ones that are gendered male. It's one of these things, all this stuff about gender. Sometimes I'm happy to have the discussions and sometimes I'm like, are we really still talking about this?
I know. It is so frustrating. I think I've been really excited to see, I don't know if you've been active on Twitter over the past few days, but this actual living scientist hashtag has been trending and it's amazing. It basically, I think it was born out of, I don't want to give credit to the wrong person. I think it was Southern Fried Scientist, but I don't want to give credit to the wrong person. But basically there was somebody on Twitter was saying, look it up. There are studies that show that something like 90% of Americans will say that they can't name one living scientist. So not only are they unaware of any quote unquote famous scientists or scientists who have any sort of public thing, but they don't know anyone in their day-to-day lives. They don't know that their neighbor down the street is a scientist or they're not, somehow connected to a university setting or industry. And so everybody is like kind of trending this hashtag where they're saying like, hi, I'm Cara. I'm an actual living scientist. This is what I do. And then usually they'll accompany it with a badass photo of them like out in the field or, wearing some crazy getup. And it's genius. It's brilliant. And it's so many women. Yeah. So many super cool women. And I think that's really all it is. It really comes down to representation because the truth is it is shifting and we see it happening. It's just happening a little in the shadows still, but not in the not too distant future. I don't think that when you sit down with a 4 and a 5-year-old and you say, what's a scientist? Draw a scientist, that they're going to always draw a white man
Doc
with a
Brown,
beard.
Basically,
yeah, and exactly, Doc Brown. Yeah, that's a good, or Einstein. Yeah. I think that will change. And part of affecting that change is talking about it, but part of affecting that change is just doing it.
Yes, so I now I get asked to, we want a female physicist to come and talk. Like, don't label me as that. I'm just a physicist. I'm doing a job. And the point about the conversations is really important because there's this idea you need some big scheme or a big thing, but revolutions start from the bottom up. Like if you're a scientist, just talk to other people and listen. And scientists are really shockingly bad at listening quite often. And it's just like, how about you just like talk to someone and just tell them what you do and don't be, I'm a scientist, or don't feel self-conscious about it. Like, I'm a scientist, I just do this. And usually in my experience, you get people like, oh, that's really cool. So there's those individual conversations, like, if you feel that scientists are not represented in society, just chat to people about being a scientist. I think that's really important. But then there is still the representation thing. So one of the things, Ada Lovelace Day, I guess, do you
Yes.
pay attention to that over
Yes.
here? So I think it's the 14th
I don't know if
of
it's
October.
as big, obviously, but I think within kind of the science and science
People are aware of it.
communication.
So it's like an extra excuse once a year for just talking about women scientists.
yeah.
And this year I was asked to do one of those, so I've written a book. So the publisher's like, oh, well, someone wants us to write a list of the 7 physics books you think people should read if they want to be a physicist. And of course, none of my recommendations had anything to do with physics, because I think the most important thing a physicist needs to know is something else. And then I didn't really think about it. And then the list happened to be published on Ada Lovelace Day. And I looked at it and went, oh, every book I recommended was by a man.
Yeah.
That's not good for Ada Lovelace Day. And then I was like, well, maybe I can make an alternative list of physics books by women. And I can sort of deal with my conscience that way. So I went looking for physics books written by female physicists, not by women who are writing about physics, although there are some excellent, but actual physics. And I think I searched and searched and searched, and I came up with 5.
Yeah.
And then I was like,
and we could probably name them all, right? Like Jana Levin's book and Catherine Freese.
Same.
And it's
that's
the same
right.
people
so it's
over
the same,
and over.
and they're obviously brilliant, but it was such a shock that even when you assume it's there and you've not found it, and then you find it really isn't there. And I found that was really shocking. And the other thing is that most of those women are writing about astrophysics.
That's true.
There's which is maybe a community that's a bit better at public engagement, but that was generally true. And there were women, who did very well further back in the astrophysics community who were reasonably high profile, and they wrote. And I don't want to think about it, but suddenly it's just like slapped in your face.
Yeah, that it's not really there. We see that a lot, I think, when we are not staffing, but when we are booking speakers, when we are putting together panels, when we are working to have some sort of event. We do a lot of kind of public planning with science communication, my friends and I think we want the narrative to be, oh, just nobody else is booking them, and so we're going to book them, and that's going to fix that. But then you realize when you start trying to book that there's less, like significantly less. And not just women, people of color. It's a huge difficulty when you're trying to say, oh, we want really good gender balance. We want really good balance of ethnic minorities within these panels and within these groups. And then you find it's the same people that are being booked over and over and over. Yeah. And it's because there are significantly less. There's already just one layer of individuals who I think are quite comfortable speaking in public and communicating their science. Not all scientists should be science communicators. They should all work on it, but that doesn't mean we should book every scientist on a television show. So you have these kind of same voices that you see over and over. And then you've got these what end up literally being like, oh, I'm the token Black woman who speaks for physics, or and it's super depressing. So not only do we need to work on, making sure that when the representation is there, that it's really visible, but affecting change at the level of the young kids so that we are producing more scientists, and scientists of various backgrounds. Because you probably remember being in school and it wasn't 50-50.
No, so I realized that my sort of the gender. So I went to a kind of a co-ed primary school, which is I can't just remember the word. Grade school,
elementary school. Yeah.
Elementary school, that's the word I was looking for. And then I went to an all-girls secondary school. So basically no gender. And then I turned up at Cambridge doing physics, basically all male, in the studying bit. So the colleges were 50-50, but so I was basically almost not even a minority because so you learn to behave like everyone else. So that wasn't gender segregated. And then I went to do atmospheric physics at Toronto for a bit, which was interesting because it was an all-female group led by a female professor. Well, there were 11, I think, of us, and 10 were female.
Oh, yeah, that's actually quite rare.
That was dysfunctional in a whole different way. Like all male environments are dysfunctional. All female environments are just as dysfunctional, just it's different. They thought I was very aggressive because I just went and did things. And they would go around and check everyone. They were very stereotypical. They would go around and check that everyone was all right before you did anything. And I just cleared off to the workshop and built it. And then they go, oh, you didn't tell us you were building it. Anyway, but so that, and then I went back to do a PhD in Cambridge, almost all male. And then I came to the States and did oceanography, almost all male. And then I went back to the UK, and then it was like, oh, now for the first time, there were women and there were men. And up to that point, there had never been two groups ever, because that was really interesting, because it's the interaction. So I never had any experience. When you were asking earlier about being put off, I never saw, there was never a large enough sample size of women or men in that one case to be a group.
And I think we don't realize how under the radar, how, when you're either in an all-girl school and you never see men, or you're in a physics program and you're one of very few women, and you just kind of put your womanness on the shelf, and you don't realize what that does to you and what sort of stereotypes you start to develop about yourself. I had someone on the show. I'm time traveling right now because I actually just recorded with her a couple of days. But as of the airing of this episode, she will have been on the show last week. And she is a material scientist, a PhD candidate at Caltech. And I think the numbers that she gave me were that at Caltech now, undergrads are basically 50-50 men and women. PhD students, it's still probably closer to an 80-20 split because Caltech is such a physical sciences school. So I do think we're seeing heavy changes. I think we're seeing that more and more women are involved. Obviously, there's always the quote-unquote leaky pipeline problem that we talk about, but there were times not long ago when undergrad physics departments had very few women. I remember when I was in grad school working on a biology master's, but we were neuroscience and we were heavily neurophysiology, electrophysiology. So we required a lot of physics interaction. We had physics students in our lab. And when we would need to machine something, the only machine shop on campus was in the physics department. And there's a PhD candidate in my lab, Mike, who would literally accompany me to the physics machine shop. He'd be like, I don't think you should go in there by yourself.
Really?
Because he was like, no, you don't understand. Like, these boys don't see girls, they're like so siloed in this. And it was terrible. But I do think that's starting to change. And I'm proud of the progress that's being made. It just needs to continue. You mentioned that book. Can you tell me once more? The
Delusions of Gender by Cordelia Fine.
Cordelia Fine. Okay, yeah, that's great. I know my listeners love, book and documentary recommendations. I've probably made this doc recommendation previously, but there are two documentaries, both by Jennifer Siebel Newsom. The first one is Misrepresentation, which is about women in positions of power. But then her follow-up, which I think was just as important, like you mentioned, The Mask We Live In, is about boys and how boys are raised to not feel, or at least not show that they have emotions, and they're raised to be hyper aggressive and and that's contributing in just the same way. So I'm glad you mentioned that. We've been talking already for 30 minutes. We have not even, we've mentioned the book in passing, but we haven't dived into it. So I want to take a quick break. I want to thank the sponsors of this week's episode. And then as soon as we come back, we are going to talk to Helen, I'm going to try it, Czerski?
Yes,
Helen Czerski once more, but we're going to dive into her new book, Storm in a Teacup, The Physics of Everyday Life. All right, let's get back to the show. All right, we're back with Helen Czerski, and we have been talking about physics. We've been talking about physics in kind of popular culture and behind the scenes. You are a physicist. You actually do physics. You also work as a science communicator doing what in the UK you guys refer to as television presenting. Here we often call hosting, discussing science in a TV platform to make it more accessible for individuals. But you're also an author. Is this your first book?
It is, yes.
That's so exciting. Okay, so you've written a book recently, and you have now an American publisher, right?
Yeah. So it's got a different cover over here.
Oh, does it?
Is very
is
funny.
This the American version?
That's the American version.
Oh, okay, great.
Yeah.
So Storm in a Teacup, The Physics of Everyday Life, same title?
Yes.
But probably all of the times when you said the word color, it now says color.
So it was more, the bit that bugged me was the day I had to go through and change all the meters into feet. The publisher wouldn't. I tried. I was like, come on, this is a science. Like, can you not even just put it in brackets? Like have it in meters, just put it in brackets. And he was like, well, why don't you just tell us the numbers? All right. And then,
That's
of course,
a
the
little
meters didn't propagate. And that was really, especially when it was like, well, can you quote the mass of the sun in pounds? No. Nobody
absolutely not.
in the history of the ever has quoted the mass of the sun in pounds.
That is I don't know if we've ever talked about that on Talk Nerdy over the 100 some odd episodes we've done, but definitely on the Skeptic's Guide to the Universe, we talk about a lot the frustrations with the English system of measurement, because of course you guys deal with it too, right?
Yeah.
We got it from you.
It's all our fault.
And you have a weird hybridization in the UK of like certain things are still on the English system and certain things are metric. Obviously, metric is always superior. Let's say that hands down.
Yes.
Always superior.
Not having a debate about that.
No, exactly. Units of 10, it's very easy to translate. And all scientists across the world use the metric system.
Even American ones.
Even American ones. And we're talking in every measurement that you can imagine. The problem is, you're right, in the public understanding, when you try to discuss something in terms of meters or in terms of grams, it doesn't always translate.
Especially if you're talking about science where people might not be feeling like they're on comfortable ground anyway.
Already, yeah. But I do like the idea of bracketing it, of saying, these are the equivalents. And still to this day, as somebody who's done quite a bit of science, there are things where I can't really visualize the difference between the English and the metric system. The only ones that I have a good benchmark for, I think, are temperature, because metric temperature is quite easy if you know that 0 is freezing and 100 is boiling.
Yeah.
You guys don't use Fahrenheit at all, do you?
No, but I was taught to my mum taught me, it's a simple conversion, right?
Mm-hmm.
So you just learn the thing.
But it is quite weird that 32 is freezing and 212 is boiling. But it is a little harder to remember things like body temperature and room temperature when you're so used to using Fahrenheit. So once you know those markers, kind of 0 is freezing, room temperature is, what is that, 30? No. 37
20,
is body temperature. 20,
21,
22. Body temperature is 37.
Yep.
And then boiling
some reference
is 100.
points
It really does start to help. It's a little tougher when you're talking about all the different things, especially complex units. Like, once you've moved on beyond mass and volume, and now you're talking density, and you're like, I don't know.
Right. Well, it's been weird. Just I've had a sat nav in the car. Driving around.
We call
LA
that a GPS.
GPS, whatever this thing is that tells you where you are and where you're going. And it keeps saying in 900 feet, turn left. And I'm like, what? I can do the conversion, but 900 feet, just
it's so
what?
random.
I know.
It doesn't even really help us. Like people, I can't really visualize 900 feet. It's like coming up soon.
Right. That's what you want to hear. It actually doesn't matter. So anyway, the book is identical, the British and I did wonder whether they'd make me rewrite. There's one bit so some of the stories are from America because I lived here, so that's all fine. But there's a bit about British coins, for example, where in Britain, half of our coins are magnetic and half aren't. If you've got a magnet, the coin, you sort of stick it in your, a bag full of coins. Some of them will stick and some of them won't, depending on what metal they're made of. And actually, the metals have changed over time. Mm-hmm. So you can actually identify which coins were made like before 1992 or something by the old ones stick to magnets and the new ones don't. And I wondered if they'd asked me to change that, and they didn't, which was quite nice.
Well, I think that's a great visualization, a great anecdote, and it doesn't translate here, does it? I don't think any of our
yours
coins
all
are
have
magnetic.
steel in them, so yours will all stick.
Oh, all of ours are magnetic. Oh,
I think so. I
try
to remember. I did look this up. I actually looked at this before I came, and now I'm jet lagged and I can't remember.
Yeah,
I think it's that they've all got steel in. It's
either
either all
funny.
or none.
It's one or the other, because there is some continuity there. We also don't have any coins, usable coins. I mean, I guess we do have some dollars, but nobody uses those.
People. Yeah. I was in the US, where I was living in the US, I think, when the dollar coins first came along. I've never seen such hatred, vitriol.
It's very
what
strange
is this? This is like the leprechaun with a bag of gold.
Yeah.
We don't want these.
Yeah. No, it's funny. I have that too, because I hate it when I travel to Europe and I end up with all of these coins that are like worth money, and then when I come back, currency exchange won't exchange them.
Oh, really?
Currency exchange will not exchange coins.
Oh,
Same at the bank often, unless it's paper currency, they won't exchange it. So you end up with all this money that you can't use.
That's
so
really funny.
frustrating.
Because what I did when I moved away from the States and I cleaned out my car, this is a terrible thing to admit. I'm a terrible human being. I hadn't really cleaned out my car for the 3 years I'd had it, not properly. And I found all this spare change kind of knocking around the bottom. But you have these machines here in like supermarkets where you just go and put in things and it gives you back some, money in some usable form. Not nearly as much fun, but you can get it. And I hate the dollar bills thing. Like I've got $1 bills floating around, and
I know it is a little frustrating. They make your wallet too fat. Yeah, if they were coins, it might be easier. And then the penny thing is ridiculous. Like, what is a penny? Nobody uses it anymore. I think it costs more to make them than they're worth. You know, everything about it is backward. Yet we keep them in circulation because we really struggle in this country. I think you guys do too, to some extent. We have a lot more in common, I think, than we have differences, but we quite struggle with conservatism for the sake of conservatism, keeping to the same old way just because it's so uncomfortable to accept change.
Yeah, it's humans, isn't it? Humans don't really like
it's
change.
It's such a human thing.
Everyone just likes to be stuck in the, stay with what you know.
So where does the title come from? What is a storm in a teacup?
The book is all about patterns, and the thing that really gets me excited about physics is the idea that it's once you've learned a pattern of physics, sort of the rules of how the universe works in one place, it applies in lots of different places. So the book is called Storm in a Teacup because there is a pattern which you see both in your teacup if you're stirring in milk, if you live in the UK, or perhaps stirring cream into your coffee if you're here in the US. And you also see it in the sky. And it's the fact that when liquids mix, they do it by swirling. They don't just, if you had two crowds of people with different colored T-shirts and you just put them next to each other, they would mix by just kind of going into each other. But liquids don't do that. They swirl around. That's the quickest way to mix. And so when you stir your tea, what you're doing is generating a swirl to mix it more quickly. And in the sky, especially at the latitudes where I live, in the UK, but you get them here as well. You get these big rotating storms, and they're rotating because, especially if it's south and north of jet stream, because you've got warm air and cool air that are mixing, and the mixing happens in a swirl. Well, that depends on whether you ask the UK Tornado Society, which does exist. So they think we get tornadoes, but most of what they call a tornado is not really what anyone else calls a tornado. We certainly do not get the sorts of things that you get here.
Do you get hurricanes?
No.
Okay.
So we just get the big stuff because we haven't got an ocean to feed the hurricanes, and we haven't got the landmass, air masses thing to feed the tornadoes. Yeah,
like we have kind of in that Dust Bowl.
But we
area.
have the cyclones that roll across the Atlantic at the edge of the jet stream, and so you get this, these patterns on the weather map which look like a swirl if you look at the fronts that is kind of going around, and that is fluids mixing, and so you can see the same physical principle in your teacup that you can see in the sky. So that's why it's called that. And it is actually, the other thing is that I think people are quite there's a bit of snobbery around things like teacups. Like teacups are an enormous amount of fun. If you give me a spoon and a teacup and some liquid, I can keep you busy with science toys for half an hour easily. But there's this sort of, it's a teacup, so it's not very important. But the same things that you can demonstrate with a teacup are also making the modern world work. They're things that citizens need to know. So it's also quite deliberately, a connection to something which is usually dismissed.
Exactly. Or that you just overlook it, even though it's right there in front of you. And in so many ways, there are these microcosms, aren't there, that we have within our own homes that are already happening. You almost don't need to invent always some sort of, go to the store and buy all these weird things in order to make a mock-up. It's like, oh no, all that shit happens like every time you make spaghetti.
And we're familiar with it. Like the thing is that these are things that everyone's already observed, and maybe they once you say it, they'll be, oh, okay, that's a thing I recognize. So all you have to do is join the dots. And yet these are the rules that make the universe work. Like you cannot overstate that. The same thing that makes toast fall butter side down tells you something about the dynamics of how the universe works. So it's not trivial. It's so important. And also it's a great, adults are allowed to ask questions. That's the other thing. Like, I play with stuff. I've got a neighbor who lives next to me who's he's got this face now, which he reserves for the times when I go, right, we're going to dye roses blue today. I need someone to come and just be a partner in crime while I dye roses blue. It's like, what are we doing now? But it's like I just never lost the habit of playing, of just looking at stuff, and I think a lot of people have, and yet you see this stuff and people are like, oh, that's once you make the connection, it's cool. People are like, oh, I recognize it.
Oh, and it's in there. It's in there.
Yeah.
Like, do you ever notice when you visit a museum that the kids engage and interact with the things that are built for kids, and they're all at kid level and they're going in, but they kind of do it for a second and move on, and do it for a second and move on. And a lot of times they're like, yeah, I already know this. Like I see this mentality in kids a lot, where you'll have maybe the museum docent at a science museum, and they'll be saying, okay, this, and the kid's like, yeah, but what about this aspect? Because they're already like so aware. And then the adults are like, wait a minute.
Right.
I have questions. Can I ask you some questions? And they're kind of like, it's like they're secretly playing,
Yeah,
and they're
yeah.
secretly like, no, but wait, let's wait to move on to that next thing, because it's there. You
Yeah,
know,
yeah.
it's there, and it kind of gives them a little bit of an excuse because they get to do it
It's
vicariously
very
through their
noticeable.
child.
They can pretend it's for the children, but actually it's for the adults. And the other thing is they get totally the same sense of reward. So there's a thing that that I wrote about in the introduction, which is, you know, if you want to tell the difference between a raw egg and a spoiled egg by boiling them,
Okay, I
let
don't know
me
what those
let me
two
start the
words
sentence
are.
again.
Yes.
So you've got 2 eggs. One of them is raw, one of them is boiled. They're both cold.
Okay.
And they're in their shells, and they're
Yes.
sitting on the table in front of you. How do you tell them apart?
Oh, okay.
And so what you do is you spin them, you put them on their side on a flat surface and set them spinning, and that's so cool. And then you just touch your finger to the top and take it away. And one egg stops spinning, and the other one stops spinning and then starts spinning again.
And that's because of the fluid.
It's because of the
the
fluid
egg?
on the inside. So people are like, once you and so what that demonstrates is conservation of angular momentum. If you stop nothing stops spinning unless you actually do something to stop it. So the other one with the liquid still going round, you know, it just pushes the shell around. And the same principle is what allows the Hubble Space Telescope to orient itself. For example, gyroscopes will keep spinning.
Yeah.
Anyway, so there's this demonstration with the eggs, and I was doing some talk. Sort of, it was a bit an odd event. It seemed to be mostly corporate people were there, you know, dressed up trying to impress their bosses. That kind of sort of audience that was quite aware of looking good to other people. And they sort of had me on, and I did a load of stuff, and I had this little video of the eggs at the end, and then I was running over, so I just kind of said, "Oh well, you know, I'll let you work that out. Ask me afterwards."
Mm-hmm.
And I had these middle-aged men in suits coming up to me, literally tugging on my sleeve, saying, "Is it this? Is it this?" And when they explained this, I would say yes. They were yes, and there's this enormous, like, you know, they got the sense of reward from working it out for themselves in the same way the kids do. And there's still everyone has fun with that.
Play is still in us, and curiosity, and it's just there are more quote unquote socially acceptable ways to do it. But adults love to do crossword puzzles and Sudoku and all of these different things that are like okay for adults to do, you know, and trivia nights at their local bar or pub, and all these different things that there are ways to do it. And I think we, as science communicators, have to tap into that better. I think that's why pub nights are so successful when it comes to public communication of science, because it's like, well, let's go to people where they already are and where they're already going to be having fun with something like that. You know, they're already showing up for this. But let's not try and take the adults to a very unfamiliar, alien, and somewhat kind of insulting place by treating them like children.
It is quite patronizing quite often. You don't have to be. It's just an interesting thing. And people are interested. What I find as I've been doing interviews about this, especially with the sorts of audiences who might not normally pick up a science book, is they are so full of questions. Like, right, okay, so that's all cool. Now, why does the Earth do this? And why does this happen? Where's magnetism come from? And what? And they're just, you know, they're thinking about things.
Even that one, you know, my background is all bio. And, you know, I got minimal physics for my bio background, but it was mostly just electrophysiology and kind of neurophysiology, like the small physics that happens within your nerve cells, and using electrodes to measure that. But that one to me has always been a black box, magnetism. Magnetism is like crazy black magic. It's amazing, and it is real science. And the poles of the Earth, you know, I have books on my shelf. There's a book right behind you called North Pole, South Pole, because I was like, I don't get it. Like, I need to read more about the little things that you just take for granted and you accept, but they're so fascinating. The reasons behind them are so fascinating. But it requires a little bit of mental effort to really get it.
Magnetism is one of the ones that is genuinely difficult unless you have the maths. And there's a great clip of Richard Feynman failing to understand magnetism for 7 minutes. And at the end of the 7 minutes, he says, if you spoke the language of maths, I could tell you how this worked, but I can't tell you. And so there are some things which are powerful. But the other thing there is that electricity and magnetism are obviously linked. The only chapter in the book that was hard to write was the one on electricity and magnetism, because we've done so well at hiding it.
Yes.
You know, you have to plug things in occasionally.
But it's all behind the walls.
But it's all behind the scenes. You never see it. And so basically there's fridge magnets and electric shocks. And that is the limit of our... And so when it came to finding... There are lots of times when electricity matters, but for everything else, all the other principles in the book, it was easy to find, what limits the height of a tree, why does a coffee stain do this? There's loads of, just too many to choose from.
But you're so
with electricity,
right. It's like you've got fridge magnets, I've got an induction cooktop, which is cool, but not many people in the US have that. They don't like it. They like a flame.
It is kind of black magic though, isn't it?
It's a bit black magic,
it's a bit sort of,
so cool.
we can't see what's happening.
And then you've got lightning strikes, I suppose, which you see visually, but you don't really interact with. And there's not a lot. And a lot of it actually is invisible.
Yeah.
So that's hard too, right?
And we've designed it to take it further away.
Exactly.
We've actually designed it out of our lives, and yet it runs everything. So yeah, but it was interesting looking for those examples and just realizing how well we've done at hiding that particular bit of science.
That one, I think that what brings me into the fascination of electricity and magnetism more is from a historical perspective. That's how I've always been quite interested in it, is the animal magnetism, the early kind of experiments with dead bodies, which were
frogs.
Quite cool.
There were a lot of frogs.
There were a lot of frogs. And then sort of the contentious relationship between Edison and Tesla and sort of the AC-DC battle, or I should say DC-AC battle, that always kind of got me and made me quite interested. But still, there was a bit of a black box kind of component to it. Well, I'm looking at your table of contents. That's my favorite part whenever I get a new book. I'm so excited to read this book, you guys. She brought me a copy. I'm so lucky. I'm going to make you sign it before.
Yes, fine.
Okay. Yes. And so I'm looking through the table of contents, popcorn and rockets. Why don't ducks get cold feet?
Very important question, that.
Spoons, spirals, and Sputnik. It's so great, these different kind of nuggets of you can see sort of how you're peering in through peepholes to start to describe some of these phenomena. Why don't ducks get cold feet? Does it take a whole chapter to explain it, or can you explain it to me now?
No, I can say to you just before I explain. The funny bit for me is the index at the back. That's when it gets bonkers, because you write the book and that's kind of cool, and then at some point someone's like, oh well, has got an index, and the index is kind of like clarinets, dolphins, trees, coffee.
Oh my God, you're right.
It's just the most ridiculous, and it's brilliant because these are all things, and they're all the stories of history and culture, and they're here and they're part of our history and our culture.
The list
is ridiculous.
Funny. Oh my gosh. Yeah, you just pick randomly. It's like cathode rays, central heating, coins, coffee, compass computers, continental drift, copper, coriander plants. Like, oh, okay. It's so random.
But that's the brilliance of it, is that these same patterns link all these things. So anyway, the ducks and the duck's feet. The problem, so I thought about this, there's a place, so Winchester in England is an old cathedral city, and it's got this small river running through it. And the ducks on the river are extremely funny because I call them treadmill ducks. But the river runs quite slowly, and they're trying to eat the grass, and they just paddle continuously. They sit there, and you watch them, and they're just paddling away and pecking at things. Then occasionally, two of them will have a fight, and they'll forget to paddle and whoosh off down the river, and then they'll really paddle really hard to get back to where they were. Anyway, so these ducks. So I went once to. So I like going to watch the ducks because it's just endlessly funny. And one time I went, the river was frozen, and the ducks were padding about on the top of it. And I was there, dressed in boots and a big coat and many layers. And these ducks are just. And I looked at their feet. Duck's foot. There's not much there. There's like, how is this keeping it fine? The rest of it's got feathers.
Yeah, it doesn't have fur.
Why is
and
it's
quite
feet
thin,
not freezing to the ice? And what they do, and more than its feet not freezing to the ice, it's how does it not just cool down the rest of them so much that they die? And what the duck does is extremely clever evolutionary solution, which is that the artery with the blood that goes down the leg and the vein with the blood that's coming back up the leg are right next to each other. And there is a law of sort of thermodynamics which says that energy will always move from the hot thing to the cool thing. So right at the top, the blood from the center is really, really hot. Yeah. But the stuff coming back up isn't quite as hot, so heat goes into the blood going back up. And further down, the blood going down is cooler, but the blood coming up is cooler as well. It's even cooler. So it's called a countercurrent heat exchanger. So basically you put them right next to each other, and the blood goes all the way down to the bottom and comes back up, but the heat only goes some of the way and then kind of loops around. But always the rule is it will move from the hot place to the cold place. but it doesn't actually have to go all the way
All the
down
way
with the
down.
blood. So
there's
the
like a
ducks,
gradient
the
of
ducks'
heat.
feet, are kind of at 5 degrees.
Whoa, so they
And
are
at the
really
top,
cold.
they're at 40 degrees.
They are really cold. It just doesn't affect the
It just
rest of
doesn't
their
affect
body.
the rest of their body. Yeah.
interesting.
So there's this basic physical law allows that process to happen extremely efficiently.
So if we had that, we wouldn't get frostbite probably. We would probably have all these adaptations that allowed our fingers and toes to operate at a lower temperature, which they do actually in humans a little bit, but there's not a big difference between your core body
Well, the other thing is
temperature
that
and
the feet of a duck don't have many muscles. They're not metabolically active quite, so they can get away with moving more slowly.
That's
our
true,
cells
They don't have
to be very
opposable
active.
thumbs or anything.
Yeah. The muscles are all higher up, so
Yeah.
it's mostly tendons and things that
It's
don't
just
need
flat pads to be able to walk around.
So it's a little bit easier. But this business of heat flow, all heat is just a word to express the movement energy of atoms. That's all it is. It's just a sort of catch-all term, but all it means is that the atoms and molecules are buzzing about faster, doing whatever they're doing, and that matters in lots of different places when it comes to how things heat up and cool down, and when you burn, why you burn yourself sometimes and why you don't, and how quickly that process happens. So it links all these little things. But yeah, everyone likes the ducks because it's one of those. It's the question a 5-year-old would ask. That's the other thing, is that adults have forgotten to ask the questions. The kids like, why this, why, and they're good questions, and you hear adults not being able to answer them.
And it's almost like there's this assumption that we should know it.
Yeah.
And so because we don't, it's embarrassing. So why would you say that in public? But like, why should I know why a duck's feet don't freeze to the river?
Yeah.
Why should I know that? Or like, the big one that people always ask, why is the sky blue? It's actually quite a complicated question, right?
Right.
And like, no, I don't expect that adults should just know that.
Yeah,
why should I expect
and why pigeons
that?
bob their heads? That's one of my favorite ones because that's the sort of, everyone's seen it. Pigeons kind of waddle around and they bob their head, and everyone just goes, "Oh, pigeons bob their heads." And but when you look at what a pigeon is doing, it's brilliant. So that's in the chapter on time, and what the pigeon is doing actually is it's not bobbing its head. What it's doing is shoving its head forward. So its head stays in the same place while its body walks to catch up, and then it shoves its head forward again. And the reason for that is that their optical processing means they take a while to form an image. So they need their eyes to be in the same place to collect enough information to get an image, but they want to keep walking while they're doing it. So what it's actually doing is shoving its head forward and catching up and shoving its head forward. And the guy who demonstrated this, I mean, the best thing about this is the ingenious experiments that people did. And this guy, whose name I've forgotten, put a duck on a treadmill. And if you put a duck on a treadmill, so its visual environment stays the same, the feet goes round, doesn't bob its head. So that's fine. You've done your little, trained a pigeon to sit on the treadmill, walk on the treadmill. And then there's this there's very rarely that, a paragraph in a scientific paper really is stand-up comedy. But there's this one wonderful footnote in this paper, which says, during the experimentation, we thought we'd turn the treadmill off. But actually we hadn't, so it was still moving extremely slowly. And what happened was that the pigeon's head slowly it was just standing there. Treadmill's almost stopped. The pigeon's head just got further and further and further forward, very gradually, until it fell over. Which is the clinching argument. Like, what the pigeon is doing is keeping its visual environment the
same. It's all of its musculature is in service to making sure that it can see.
And what that tells you is something about the nature of time, because, we laugh at the pigeon, but we only see a little bit more quickly than that. So there's all this stuff in the world that's happening just too quickly for us to, like, it's like if you're out on a run. I go do quite a lot of sports. So I'm out running quite a lot. If you see anything interesting, if you really want to look at it, you have to stop.
Yeah. Oh, absolutely.
So we're only a little bit faster than the pigeon. And so then what that says is that there's a huge amount of stuff that happens just slightly too fast for us to see, and also a lot of stuff that's very, very slow. And so time is interesting because we sort of assume that we work at the speed that things work at. And actually, we're really complicated. The world's doing all these little things, just getting on with it, these little simple tasks, just too fast for us to see. And so time affects. If you try and do something slowly, that works different from when you try to do them quickly, for example. So the way a snail moves, so a snail's got all this mucus, on the bottom of its foot. And it's hilarious. It's one of those questions a kid asks, like, a snail, how is it moving, right? It doesn't walk. It's just not lifting. It's not like a caterpillar. It's not lifting any bits up and putting them somewhere else. What is going on? And the snail's mucus is it's shear thinning, which means that its gloopiness depends on how fast you do things to it. So if you move it very slowly, it's super fast and thick and gloopy, and it just kind of, it's sludge. But if you can get it moving quickly, it becomes really runny. So it moves really quickly.
It's like a non-Newtonian fluid.
It's a non-Newtonian fluid, just like ketchup. And so what the snail does is round the outside of its foot, it's moving very slowly. So that's all quite sludgy. But what it does along the center is it's got these bits of muscle that sit in there that shove forward very quickly. So the outside kind of anchors what's going on, and the inside bits, now they never leave the surface, but they just shear fast enough that the mucus becomes runny, moves that bit of the snail forward. And then, so the snail's kind of walking, but it's not doing it by lifting up a foot. It's doing it by controlling the properties of its mucus with speed so that some bits are really slippy. And the whole snail can move along. And there's these wonderful experiments that were done on it by putting a snail on a glass sheet and taking photographs from underneath, and you can see the different bits moving at these different speeds. But the point is the snail is controlling it by controlling the speed at which it's doing things. And so time matters in physics. It's not just something that, there's more time or less time.
Yeah.
That speed matters. So there's all these funny little things in everyday life that
we don't. You're right. That
connected.
we almost can't. We might not have the apparatus to process, but we've invented all sorts of cool tools that allow us to. I remember going to the American Museum of Natural History in New York 5 years ago. Maybe they had an IMAX movie that they were showing. I think it was with like 3D glasses, and it was all about the things that happen too fast, too slow, not in perceptible kind of color vision, all these different sort of just outside of our capabilities with our senses. And they used all sorts of cool photography to capture them, time-lapse photography and super slow motion and all of that. And you could really see just how alive everything around you really is. You could see breath clouds coming out of individuals. You could see growth of plants, just things that aren't quite within our perceptible realm. And it was so stunning because it was, I don't know, there's so much activity all around us all the time. And I think that really goes back to what you mentioned about basically so much of what our central understanding of physics is just about atoms bouncing around, right? We can't see it happening. We don't know, the difference in heat and cold, or the difference in a solid versus a liquid versus a gas is really just about all these little individual tiny things. How quickly are they moving and how much space is in between them? We don't think of it that way because that's not on the human evolutionary scale.
But then once you start to see the evidence for that model for the world, these atoms moving around, you also have access to things like how the latest electricity generates. So wind turbines, for example, how they work, how insulin tests work, these things that citizens need to know. You have a direct link through from all these everyday stories to something which we would argue this is, even if you think that science is trivial or whatever, even if it doesn't interest you, but you care about things that matter, if you want to do things in the world, these are the things you should know about. And so the last chapter of the book, so what my sort of view of things is that each of us has 3 life support systems: a body, our planet, and our civilization, the infrastructure of our civilization. Each of those systems are keeping us alive. And the reason why something like climate change, for example, is a problem in that worldview is because the life support system of the planet and the life support system of the civilization are kind of butting up against each other. You have to negotiate the boundary. So the thing is that then these patterns, these physical patterns that are showing how the world works, these are the rules that are running those life support systems. So if you're interested in keeping yourself alive, there's all the stuff about science being interesting and fun and curious, which it is, awesome, but it's also making the world go round, quite literally.
Yeah.
And so if you're interested in like how to run, how to look after, to steward our life support systems, these same rules, the things you can demonstrate with teacups and coffee stains and putting raisins in lemonade, they matter for that view of the world. And so there's also, this, it's not just that it's accessible, it's that on the sort of grandest possible view you can have of humans, these things matter. And it's not trivial. But you can get there by having fun with raisins.
Yeah. Science really is modern philosophy in so many ways. It's a way to interrogate and understand what's happening around us that is like reproducible, which matters. But it comes back to the same core questions we've had since the beginning of civilization, right? Since before the beginning of civilization. The really big picture questions about our place, our relation to one another, our relation to the universe, time, death, all of the things that we, sometimes try to avoid contemplating because they can be kind of scary. But when we embrace contemplating them, they bring us, I think, value. The Sagan spirituality,
Right.
the secular spirituality, which is fundamentally important. And we all go there. Everybody goes there from time to time, even if they're forced to go there because some life event, takes them to that pondering place. I think scientists love to go there all the time. There's like a morbid curiosity with our sort of temporalness, I think, but it is so fundamental to being human to ask these really, really big questions. I think on that note, I'm going to ask you two big questions because I do end every episode by asking my guests the same two obnoxiously big picture questions. So I would love to hear your take on them. As it's funny, we never even talked about your research. I mean, you mentioned it. You mentioned the bubbles.
Bubble physicist is a real job. That's the important
I
bit.
love that you're a bubble physicist. I also am fascinated by how bubbles are so important for so many aspects of physics. Like you study bubbles in the ocean, but cosmologists talk about bubbles when it comes to multiverses. It's like there's so many ways, and bubbles in your bathtub directly translate to surface. There's a million things, and yeah, bubble physics. It's fascinating.
So, I mean, just a little bit on the bubble physics
we have
time
to.
is that because bubbles are the sort of the unsung heroes of the physical world, because what they do, they're a place where a liquid and a gas. So I'm talking about, gas bubbles in liquid, not soap bubbles.
Mm-hmm.
But they're a place where they can't mix. They're basically trying not to mix. And what's interesting about that, so imagine a coffee with a sort of cappuccino, cup of cappuccino with foam on the top. If you get I saw coffee snobs, I'm sure they're lovely people, coffee aficionados, one's balancing a spoon horizontally on that foam and counting the length of time it took to fall through as a measure of how stiff the foam was. Now, that is a fascinating thing to do, because if you just took a cup of coffee and you put a spoon on top, the spoon would fall in.
Yeah.
If you took, some air and put a spoon on top of it, the spoon will fall through. Mix the liquid and the gas together, and suddenly you have something that can hold up a spoon.
Yeah, you've got a real structure.
That's why bubbles matter. It's because they allow the combination of a liquid and a gas to do something that neither one can do on its own. And so the bubbles that I study in the ocean that are helping the oceans breathe, it works because of that extra thing that comes along. They're used in medicine as contrast agents and for various other things in industry. And they're everywhere, and they are these workhorses that they're a mechanism. They provide a mechanism for physical processes that wouldn't otherwise happen, and they're fascinating. And they're right here.
Fascinating, yeah. That additively they're greater than the sum of their parts. They offer principles that are greater than the sum of their parts. That said, they are so important and so necessary, but they also can be ruinous to your experiments as well.
See, I like bubbles, but what I have discovered, there's a lot of people who don't.
Yes, I can attest to when I was working as a cell culture technician and trying to navigate these very delicate kind of fetal mouse tissue, like these fetal brain cells, and coax them to grow, outside of the body. Bubbles destroy tissue. You have bubbles into your solution and you're not careful, they can rip through very sensitive tissues, and they can introduce gases to a kind of otherwise stable solution that can be ruinous. So it's interesting that they're a vehicle for good or bad.
Yeah.
Like much technology, right?
Yeah.
I love that. Thank you for indulging me for a couple minutes to go there. Okay, so I like to close every episode by asking my guest to let me know what their deep thoughts are about the future. And I basically frame it in two different questions. The first one is that when you think about the future, and you can answer it in whatever context is important to you. It could be personal, or it could be like super big picture, beyond global if you want it to be. But what is the thing, if you had to pick one, that is most disconcerting to you, that keeps you up the most at night, that makes you most worried about the future? And then on the flip side of that, just so that we're not crying when we end the podcast, what is the thing that you're most kind of hopeful and optimistic and excited about?
The thing that worries me the most is the management of these 3 life support systems, that we have to take seriously the idea of maintaining them and making them better, because they are life support systems. And bothers me, I think, that they're taken for granted. Like we said with the technology at the start, I mean, we've never had to worry about what our planet does, really, just kind of does stuff. But now we're in a position where we are managing it. And it is still this great engine that's doing things, but we need to appreciate what it's doing. And the same with the infrastructure of our civilization. We need to appreciate, roads and bridges and networks. So I think the thing that worries me the most is that we are taking our amazing technological understanding so much for granted that we might neglect the life support systems that are keeping us alive. And now that humans are so populous, it's not, you can't assume it's going to be all right, because we have to actively manage what's going on. So that's the thing that worries me the most.
Yeah.
Which is a very, it's one of those things you have to not think about too hard for too long.
Exactly, because it's even more than climate change. It's all of the different ways that we've not been stewards and that we've not been very good at interacting. And, it's beyond climate change. It's beyond war. It's beyond all of these things. It's a network where everything kind of affects the other.
Yeah, and they're interlinking. The fear of complexity is holding us back, and all the an obesity epidemic, or sort of things falling apart, all of that. So appreciation of those systems, I think, is, and it is just a case of not being afraid to appreciate them. So that's the thing that bothers me. And to move on to more positive things.
Yes.
The thing that that excites me, I think, about the future is that, and I don't know, it's hard. It's such a general statement.
I know,
but is that humans are capable of so much, that the creativity and ingenuity. And the thing is, it's not just about, oh, someone's going to invent a device. I'm not even talking about that. They're capable of being nice to each other. When you see someone on the street drop something and you pick up their glove and you give it them back. Someone did that to me on the subway the other day. Those little human interactions that make other humans happy. We're capable of so much, and that even if you feel helpless in the world, you can always be nice to someone. You can always go and tutor a class. There's always little things you can do that make something positive. And there are big things that go out of the little things, but it's all about the little things. And I think that is something that makes me excited, that it's, there's all this talk of big ideas. It feels like the fashion house, you've got to have the biggest idea that's going to solve the world and cure cancer and do these things. But actually, the only way that's a hindsight thing.
Yeah.
The way you get there is just doing a good thing now. And the fact that progress can be made just on the basis of doing one little good thing now, and then doing the next little good thing and doing the next little good thing, that makes me optimistic, because you do need the big picture thing, because you kind of need to know where the problems are, to where you're working. It's not that you should be undirected, but you can make progress by doing something manageable and by being a decent human being while you're doing it. And that's a really good thing.
And it's funny, because they really are in many ways like ripples on a pond. There are these propagating events, like something quite small that you might forget about 2 seconds later could affect downstream so much, and it could gain so much momentum that it could really become something much larger.
And it gives people permission. If humans see one person behaving well, it kind of gives them mental permission also. So it's also like compound interest in that if you make a bit of effort to do the good thing now, other people will see that and they will do the good thing. And that's such a powerful thing.
Yeah, we are such social creatures, aren't we? And we're so easily influenced by our peers, even individuals we don't know. We're so quick to mimic, and in a very bad way or a very good way. And so just making that conscious kind of mindful decision to do something positive, it can affect it's a full butterfly effect. Like you could probably do some fun experiment where a TV show where you measure the actual physical changes across it, and then it caused this person to do this, and then so and so did this, and eventually
and hope it doesn't all end up like Lord of the Flies with them all on some island killing pigs.
But it is. I love to think about it that way. I don't know. It's fun to romanticize it, but I don't think it really is romanticizing it. It's true. It actually happens that way. Oh, Helen, this was so much fun. Thank you so much for being here. I want to make sure that everybody knows that they can buy your book, Storm in a Teacup, The Physics of Everyday Life. It's available everywhere now, right? It's already been released here in the US. So yeah, anywhere where books are sold, go to your local bookseller first, guys. But then if you have to, you can go to a big box place. And I want to know, like, let me know what you're kind of doing right now, where people might be able to see your work, and also where they can find you kind of via social media to say hello.
My Twitter handle is Helen Czerski, and my surname is spelled Czerski. There's not very many with my name, so I'm quite easy to find. If you put Helen and Bubbles in, that also gets you to me. I write. I have a column in BBC Focus magazine. I'm about to do some writing for the Wall Street Journal, a column on everyday science. And so I do TV, so I pop up on that. I've just done a series on the physics of sound, which will be out soon in the UK. I don't know where else it's going to get to. I also am about to go on tour in Australia with the Cosmic Genome Project, which is Robin in some his amazing network of fascinating people. So a few of us are going from Britain to Australia. We're going to meet local Australian artists and put on these big shows. So if you've got any listeners in Australia, we will be all over Australia and New Zealand doing these shows in March and April. And they're just fun. It's like a mixture of science and art and comedy and music, and they're brilliant shows. So that I'm really looking forward to that. And yeah, I can genuinely be found being enthusiastic about science on Twitter. That's probably the best place to find me.
Awesome. Well, I'm honored that you took the time to sit down with me and to share your love of physics, which I know is affecting many, many people the world over, actually. So thank you for sharing your story with us. Thank you for being here today. And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we can all get together to talk nerdy.